Hello everyone, welcome to the 20th lecture in this series. In this lecture, we are going to learn about a new data structure which is trees. Tree is an example for non-linear data structure. Hope you remember in the very first lecture on this series, we learned about two broad categories, linear and non-linear, and tree is the first data structure which we are learning under the category of non-linear data structures. With linear data structures, you know, the elements have to be stored in some sequential manner, and so for every element there will be a preceding and a following element with respect to storage. But in case of non-linear data structure, it is not going to have a sequential representation in storage, rather it is going to have some hierarchical representation. And so we will be learning about some of the terminologies associated with trees in this lecture first, and after that we will be diving into binary trees, which is actually a type of tree, and what are all the types of binary trees available we will be seeing, and then we will be moving on to the representation of trees, and we will be seeing some of the examples. So, this is the organization of this lecture. First we will see what nonlinear data structure is, then we will be seeing some of the definitions as available in some of the books, and then we will be moving on to some terminologies associated with this data structure, and then we dive into binary trees, its definition and types, and then we will be seeing the representation of trees with array and linked list representation, and finally we have some questions to test our understanding. So, tree is a non-linear data structure, and as I said, it is a hierarchical structure. So, here the data is stored in a hierarchical fashion. So, in every tree there will be a root, and there will be some other subtrees followed by the root, right, and in every subtree there will be a parent and child relationship between nodes. There will be some nodes which are designated as parent nodes, and nodes may have child or children. And so, in order to link all of these, we will be having a set of edges. As such, when you talk of trees, we will say that the entry point to a tree is root, and then it will have some subtrees, and where every subtree will follow a parent child relationship, and all the nodes are linked by means of edges. By edges we mean actually the references which are pointers to some other nodes in the tree. In real world, when we see trees, you could see leaves, branches, trunk and root, but in case of tree data structure, you should visualize the tree in an inverted manner. So, you should think of trees in an inverted manner such that root lies at the top and branches follow it, and towards the end we will be having the leaves. So, the entry point to our tree is the root. From root we will be accessing all the interior nodes, and finally the nodes at the leaf position. So, we define trees recursively as a set of one or more nodes. Among the set of nodes, one of the nodes is going to be the root, and it is going to mark the entry point for the tree. So, for accessing any of the trees, we need to know the position of the root. So, we have learnt already with linked list, whenever we want to access a linked list, we usually keep track of the head pointer, right, and we always start accessing linked list from the pointer or the node being pointed to by head, right. So, in a tree we always need to know the reference or the location of root, and from the root we will be able to access all other nodes in your tree. And every tree will be organizing nodes in a tree as three sets. First is the root, and then there will be some intermediate nodes, and there will be some nodes which are called as leaf nodes. So, all nodes in your tree will usually fall under these three categories. Of course, for a tree there will be only one node called root, and there can be any number of intermediate nodes, and there could be any number of leaf nodes. And by nodes, what I mean to say is, in a tree every node will have some value, and every node will also have some pointer references to its child or children nodes. And the key point to be noted here is none of the reference is duplicated. So, here the meaning of that none of the reference is duplicated is that for any child there can be only one parent. So, for instance, if there is a node at called n and there is one node called m which is its child. So, m can have a reference or a link from n, and always n will be holding the reference to m. So, that is why we say that any node can have only one parent, and so we say that the reference is not duplicated. And in a tree there can't be any cycles. By cycles we mean a closed path. Okay, we have a set of nodes and there can't be any closed path in a tree. In the later part of this course we will be learning one more data structure called as graph. And when we define graph, we mean to say a graph is a set of nodes, and a graph will also have set of edges that link various nodes. So, the primary difference between tree and graph is that in a tree there is no way of having a cycle, whereas cycles are permissible in graphs. So, what we can say now is that every tree will be a graph, can be called as a graph, but not every graph is a tree. So, now we see the definition of a tree. Tree is a set of nodes, and at times your tree can be empty initially. So, we say that it is an empty set of nodes, or otherwise your tree has some elements, and among the set of nodes one will be called as the root, and followed by the root we can have 0 or more trees which we call it as subtrees, and those subtrees usually descend from the root. And the tree has plenty of applications. The very best example I could say is the way your files and folders are organized in your system. You could have witnessed, say, when you click on my computer and when you look at the way your storage is organized, at the top level you could see that your storage is organized into set of drives, and when you dive into any of those drives you could see many folders, and within folders you can have subfolders, and within subfolders you can have files. So, your drive D or E, whatever it is, that can be thought of as a root, and your folders and subfolders can be thought of as intermediate nodes. At the last level you have the leaf nodes, which is actually your file. So, likewise your tree data structure has plenty of applications, and here in this slide what you see is one another application of tree with respect to evaluating expressions. You know, in any language, if you write some code and if you have some expressions to be evaluated, that is usually evaluated by constructing an expression tree first. An expression tree is actually a binary tree, and in an expression tree you could see that all the parent nodes are all operators, and all the leaf nodes are all operands. This is what I mean as parent. So, all of them are operators, and leaf nodes are ones that do not have any children. And so, here you could see that A, B, C and D are all operands, and so they do not have any children. So, the way in which this expression would be evaluated is C/D would be done first, and its result would be multiplied with B, and that result will be added up with A. So, that is how this expression has to be evaluated. So, here this is what your most of the compilers use. Usually compilers make use of trees to handle or evaluate expressions. So, when we use this tree structure, there is no need for parenthesis to prioritize the way this expression has to be evaluated. So, here we see one more definition for tree. So, tree is an abstract data type. So, abstract data type in that sense, there are set of operations that are permissible on a tree. So, we will be learning it later, and there will be only one entry point to a tree which we call it as root, and every node, any other node other than the root can be either a leaf node or it can be some internal node. And every internal node can have some children, it can have one or more children, and those children can be directly reached from their parents, which are again some internal node. So, here in this diagram what you see, you could see that one node being designated as root node, and you can think of the tree to have some levels, or by levels what I mean is that the bubbles you see in every row. Here in this tree you could see there are 3 rows. In the first row you could see there is only one bubble, which is the root node. In the second level you could see 2 bubbles, and that make up the internal nodes. And in the last level you could see, last row you could see 3 bubbles, and they don't have any children, right? And so we call them as leaf nodes. So leaf nodes are one without any child or children. And here when you take up level 2 or the second row, you could see that this bubble has 3 downward arrows, which means this node has 3 children, and so for these 3 children this node becomes the parent. And when you take this node into account, it does not have any descendants, we do not have any downward arrows, and so this is also treated as a leaf node, and for this node root node is the parent. So as such, for these 2 nodes root node is the parent, for these 3 nodes this internal node is their parent. So this is one another definition for trees. A tree is a connected undirected graph. So by connected we mean that there is some link between the nodes, and undirected in that sense it can be usually the edges are all undirected, that is without any direction, that is pointing to upward or downward, there is no direction. And this is the definition of tree in terms of graphs. We say that a tree is a connected undirected graph with no simple circuits. So by circuit we mean to say that in a tree there can't be any cycles or any closed path. And the characteristic of a tree is that there can't be multiple edges between nodes. So when I take into account any set of nodes, any pair of nodes, say a parent and a child, between them there can exist a maximum of only one edge. So we say that multiple edges are not possible, however this is allowed in graphs. And in a graph, in a tree, you are not supposed to have any loops or cycles or circuits. And there are certain other properties that should be true for a tree. One is that the entry point to your tree is your root. So always you need to know the root node from which you can access all other nodes in your tree. And all nodes except the root have one parent. So that is what I said earlier, every node can have a maximum of only one parent, but this is not true for root. And traditionally trees are drawn upside down. So that is what I said, you need to visualize trees upside down, so that root is at the top and leaf is at the bottom. And these are some of the terminologies associated with trees. So in your syllabus you are given with binary trees, binary search trees and threaded binary trees, and of course whatever be the tree use, these terminologies are true for any tree, and so we will be learning these terminologies first. And first is the node. So I told you the tree is a collection of nodes, and just as we define the node structure for linked list, that is single and double linked list, we need to make node definitions for tree as well. So when we make node definitions for tree, we need to know that every node is supposed to hold some data value and is supposed to hold some reference, and that reference corresponds to its children. So in later part of this lecture you will see how to make node declarations for a tree. And root node, you know, it is the entry point to your tree, and all other nodes, say internal nodes or leaf node, they are usually descendants of a root node. And you will have a parent child relationship in a tree. and as I said, a tree may have many levels, and for any nodes at any higher level, its parent would be in the previous level, right? And for us, any intermediate node can be treated as a parent node, and all other nodes that are its descendants are treated to be a subtree. Say for instance, if from the root node, if the root node has two children, then we will say that the tree contains two subtrees. One is the left child of the root node, and other subtree is the one at the right side of the root node, with the right child of root node being the parent of the right subtree. And we can have children or any number of you can have any child or children nodes. So for example, depending upon the trees we use, the number of children would vary. At times you can have a node with no child or children. At times you can have a node with n number of children. And for instance, if you specifically deal with binary trees, then there is a condition that a node cannot have more than two children. So it could have either 0, 1 or 2 children. And we will be having some nodes as leaf nodes in your tree. And how to identify that node as a leaf node is that it is a node without any descendants. So then you need to know what is the degree of a tree. So degree of the tree is the number of direct children a tree or a subtree has. So here for computing the degree of a tree, we need to compute the degree of every node in the tree first. So we need to check the number of edges that emanate from every node, and the whatever is the maximum value, that is going to be the degree of the tree. So here yet another term which you need to know is levels in a tree. So here whenever we talk of levels, we just talk of arrangement of nodes row by row in a tree. So we always say that root is at level 0, and the next set of internal nodes would be level 1 and level n and so on. And so here in this example, as you see, your root is at level 0, and this set of nodes make up level 1, and the last two nodes make up level 2. And as you see here, these are the nodes at the intermediate level, and we say that we have parent child, they have parent child relationship. For this parent node, there are two children, and these two nodes are called as leaf nodes just because they don't have any descendants. And consider these two intermediate nodes, they are themselves leaf nodes just because they don't have any descendants. And root is this is the root node, and the root node has three children. In other words, we can say that these three nodes parent is the root node. Now we will see some more terminologies. The first one is edge. I told you that a tree is a collection of nodes, and the edges and the links to the nodes are what we call as edges. So we say that it is the line connecting a node n to any of its successors. So we say that the line starts from parent and ends at a child. So we say that it is a line from a node n to any of its successors, and that is what we call it as an edge. Next is what a path is. So a path is nothing but a sequence of consecutive edges. Say for instance, I start from node A to D. So I have A, B, C and D. Imagine that we have four nodes A, B, C and D. So for B, A is the parent, for C, B is the parent, for D, C is the parent. So in that case, if I want to compute the path from A to D, I need to count the number of edges between A and D. So in our case, A to B there is a path, there is an edge, B to C there is an edge, and C to D also there is an edge. So we have three consecutive edges between A and D. So here that is going to be our path. A to B, B to C and C to D is our path. And then the term in degree and out degree. So in degree means the number of edges arriving at a node, and out degree is number of edges leaving from a node. So, by trees, in a tree you know very well that every node can have only one parent. So, for any node in your tree there can its in degree should be 1. Whereas, if we talk of trees in general, there can be any number of children for any node, and so when we say out degree it could be any number of edges leaving from that node. So, for instance, if a node is a parent to 3 child nodes, then its out degree would be 3. The next terminology is what depth and height are. These two are very important characteristics which usually helps to define a tree. So, depth is nothing but the depth of the node is the length of the path from the root to the node n. So, the depth of the root node is always 0. So, we always calculate depth from the root. So, from the root we actually count the length of the path from root to the any designated node. So, you could have any number of levels in your tree. In order to compute the depth of any node, we need to count the path length from the root node. The next definition is what is the height of the tree. So, it is the total number of nodes on the path from the root node to the deepest node in the tree. So, always we measure height from the deepest node in the tree. So, your deepest node should be any of the leaf nodes in your tree. See, we count the total number of nodes. So, we will be counting from the deepest node to the root node. So, whatever be the total number of nodes along the path, we call that to be the height of the tree. If suppose your tree contains only one node and that is the root node, then we say that the tree's height is 1. And then about level number in a tree. As I was mentioning before, we usually arrange or we usually view the nodes in a tree as some set of nodes placed in some rows. So, we always position root node in one row or the first row, which we call it as level 0. Then if we have more number of intermediate nodes, so depending upon the number of nodes in which we have intermediate nodes, we will be counting that as level 1 to say level n. And at the bottommost level we will be having some leaf nodes, and leaf nodes are ones do not have any children. So, that makes up the last level in your tree. So, when you look upon a tree, your root node will be you will be starting to label root node as level 0. Consequently, the next levels will be numbered from 1 to n. And then what a parent is. So, for example, if n has a child node n1, then for n1 n is the parent. So, as I said before, always among the set of intermediate nodes there will be parent child relationship, and whatever node is a successor to a node, that is called as its child, and this node becomes its parent. And then about sibling. So, sibling means for those nodes that are on the same level, and if they share the same parent, we call them as siblings. So, this is true for trees as well as for binary trees. Say here for instance, we have one node A and we have 3 nodes whose parent is A, then in that case both B, C and D, all of them are called as siblings, as just because they share the same parent node. And ancestor node is one for which any parent node can be called as an ancestor node to its child or children. So, here any predecessor node on the path from the root node can be called as ancestor node, and if a node happens to be a successor on the path from node to leaf, then it can be called as its descendant. So, in a parent child relationship, any parent can be called as whatever nodes that appear in the level above the said node, that can be called as its ancestor, and whatever nodes that lie along the path from this node can be called as its descendants. So, here we have some more terminologies like siblings, which means two nodes having the same parent, and you know what edge is, it is the link from one node to another, and I told you what path length is, which is the number of edges that must be traversed from one node to another. So, here we will see with an example. In this tree what you see here, 0 is the root node, and whatever arrows you find in this tree, all of them are edges. In this diagram we have shown them with the direction, but usually in trees actually these lines will be without arrowheads. So, which means we say that it is undirected. And here for 1 and 2, 0 is the parent, and so we can call them as siblings. And here 4, 5 and 2 are all root nodes, just because they do not have any descendants or any children. And if you want to know the path length from root to 3, then we need to count the number of edges from the root. So, in this case they have computed the path length of 4 from root. So, from 0 to 1 there is one edge, 1 to 3 there is one edge, and 3 to 4 there is one another edge. So, totally the length of the path is 3. And if we talk of levels, as I said before, root is always designated to be at level 0, then 1 and 2 are at level 1, node 3 is at level 2, and nodes 4 and 5 are at level 3. So, 0, 1, 2, 3 is the level numbering which we give. And when we talk of parent and child, for 4 and 5, 3 is the parent, for 1 and 2, 0 is the parent, for 3, 1 is the parent, and vice versa we can say for child or children. And when we talk of descendant and successor and ancestor, for 3, 4 and 5, 1 is ancestor, 4 and 5 are all descendants of 3, we can say that way. And for root, all of them are all descendants, for all of them root is an ancestor. And now we learnt about depth, and you need to know, whenever we talk of depth, we just compute the path length from root of the tree to this node. So, if you want to compute the depth of the node 3, then I should start counting path length from root, which is 2. Then height of the node is actually the maximum distance of any leaf from this node. For finding the height of the tree, we usually look at the node at the bottommost level or the leaf node. So, we start counting from the bottommost level, and that makes up the height of the tree. So, when you talk of leaf node, it is at a height of 0. When you talk of root node, it is at a depth of 0. So, usually height of the tree is the height of the root of that tree. So, both will be usually equal. And descendants, as you know, any nodes that can be reached via one or more edges from this node can be called as its descendant. Say for instance, if I want to reach 5, I can reach 5 following the node from 1, right. So, thereby for 1, 5 is a descendant. And likewise, whatever nodes that lie, I mean, in order to reach this node 4, I need to follow the path from 1, right. So, there is no other way to reach this node 4. So, here in this case 1 naturally becomes ancestor of 4. And then about subtree. So, a tree whose root itself is a child of a node, it can be called as a subtree. You know very well that in a tree the entry point is root, and so for any node which is a child of so here we see the definition for depth. So, depth is always computed from the root of the tree. So, if you want to compute the depth of any node, you need to count the path length from root node to that particular node. If you are asked to find the depth of the tree, then you should find the path length from root to the deepest leaf in the tree. Next is what the height is. So, height of the tree is actually the distance from the leaf node to the root. Say for instance, if you are asked to find the height of the tree, then you should start from the deepest node to the root, and if you are asked to find the height of a node, then you will be computing this from the particular node to the root. So, we always say that a leaf node is at height 0, and we also say that a root node is at depth 0, and always the height of the tree is the height of the root of that tree. And other than that, we learnt about ancestors and successors. Also we can say them as descendants. So, for instance, whatever nodes that can be reached via a particular node are all called its descendants, and whatever node that lies above that particular node and lies along the path from that node to the root can be called as its ancestors. Say in this example, if you think of node 5, all these nodes along the path from the root can be called as its ancestors. And if you talk of node 1, whatever nodes that are along the path to the leaf from node 1 can be called as its descendants. And to here we see the definition for subtree of a node. You know what a subtree is. You know the root is the entry point for any tree, and if suppose your root has 2 children, then those nodes that are following the 2 children can be together collected as called as 2 subtrees of the root node. So, its left subchild together with all its descendants make up a subtree, and its right child along with all of its descendants make up the right subtree. And we also discussed about level of a node. So, you know always root is at root is labeled to be at level 0, and all other for finding the level of all other nodes, you should always add up 1 plus the level of its parent. Naturally, any child will be at level plus 1 than its parent. So, here we see again the height and level here. We know the definition for height as well as what level is. So, here we have a tree, and the question is whether we can decide or compute the height of a node recursively. Yes, we can very well do that. In order to compute the height of this tree, what you need to do is you have to compute the height of its left subtree and height of its right subtree. So, in this case, if you compute the height of the right subtree, then we need to start from the leaf node. So, it is going to be 1, 2, 3, 4 and 5. When you look at the left subtree, we have only one node. So, when we talk of levels, this is 1 and this is 2. So, this is actually 2, and here the standard way of recursively defining the height of the tree is that we compute the height of the left subtree and height of the right subtree. We take the maximum of that. So, in our case the height of the right subtree is maximum, and together we need to add up a value of 1 to account for the level 0, which is root. So, if we find the height of the right subtree, then it is 1, 2, 3 and 4 in our case. So, this is 4, and height of left subtree is just 1. We have only one node which is B, and so the height of the left subtree is 1. So, the maximum among that is 1 and 4 is 4. To 4 we add a value of 1 to include the root level, and so the height of the tree is going to be 5 in this case. So, this is the standard way of computing the height of the tree recursively. So, with this we can conclude that we have seen some of the definitions for trees, like we started with what a node is, what edges are, what is the height of the tree, what is the depth of the tree, what a level is, what is an ancestor, what is a descendant or successor. We learnt what edges mean, and then we even learnt what a parent child relationship and how it exists among nodes in a tree. And we learnt that any tree has one root node which makes up the entry point, and there can be set of intermediate nodes or internal nodes, and there can be some leaf nodes where leaf nodes do not have any children. So, we will be continuing with the rest of this presentation in the next lecture. Thank you.